Okay, so here is our little Mathematica code for Shor's algorithm. So, and we're doing this, we're just going to find numbers that work. So the first thing we do is we take the third prime and the fifth prime. Those happen to be 5 and 11. And we multiply them together to get 55.
Okay. All right.
Okay. So now we're starting with a number. And so in our little program, we already know what the prime factorization is. This is just what Kelsey Houston Edwards did. We're just trying to understand how the process works. So the very first thing we have to do is select a number, A. Okay, so since we've already done this once to make sure the program is working, let's pick a new A.
Okay.
So pick a number less than 55.
How about 31?
31. Okay. The first thing we have to check is the greatest common divisor, and it tells us the greatest common divisor. Oh, I should have put 31 and 55 in there just to make sure we were evaluating, but it tells us the greatest common divisor is 1, which is what we want.
Okay.
The next thing we have to do is compute the period of 31 mod 55. And what is that? What are we doing when we compute the period of 31 mod 55?
So we're looking at 31 squared, 31 cubed, all the way up. And we're taking all those numbers mod 55 and seeing when one of those numbers equals 1.
Okay. So it's very, very straightforward. We start with a counter set equal to 1.
Okay.
And we evaluate mod a to the r. A is 31 to the r, mod our number, mod 55. And while that's bigger than 1, we just keep looping and increasing the value of r. And whenever it is equal to 1, we just stop and it tells us what the period is. So the period of 31 mod 55 is 5.
We want this to be even. Right?
Ah, but unfortunately we need it to be even.
We have to choose a new number.
So we have to, so 31 doesn't work for this algorithm, but that's okay, that was easy. So we gotta pick a new number. So pick something other than 31.
How about 40?
40.
Actually, no, not 40.
No,
but,
it's okay, 40. The greatest common divisor is 5.
so it broke there. So
Yeah.
how about 41?
41, okay.
It's 1.
Greatest common divisor is 1. Now we go back down to here. The period of 41 mod 55 is 10.
So that works.
Okay, and then we have to also check that a to the r over 2 plus 1 mod n is not 0, but it's 22.
22.
So we're good. And the last step is we evaluate a to the r over 2 minus 1, a to the r over 2 plus 1, and compute the greatest common divisors with 55. And we're hoping in this case to find 11 and 5 again. We find 5 and 11.
Cool.
That works.
So that's actually interesting. The first time we did it through to make sure the program was working, the first prime was 11 and the second prime was 5.
Now it's switched.
Now it's switched. So a to the r over 2 minus 1 and a to the r over 2 plus 1 are only guaranteed to produce the primes,
Not in any particular order.
but not necessarily in the right order. Okay?
Yeah.
Actually pretty fun. So now, but that was for a small example, like Kelsey Houston Edwards did. Small primes 5 and 11. Let's go an order of magnitude larger in the prime count. So we'll do primes 30 and 50. So now we're doing, the primes are 113 and 229. So we have this number,
This big.
25,877.
Didn't you say the inscriptions only had 2 prime factors?
That's right.
But you chose like 30 and 50.
Oh, sorry. This is the 30th prime.
Oh.
This is the 30th prime. 113 is the 30th prime.
Okay.
229 is the 50th prime.
So we should get 113 and 229.
Right, our n that we're using here is 113 times 229, which is 25,877. Which if we were just looking at this number for the first time, we would not know how to factor that number. Because, have you memorized your 113 times tables?
No.
No.
No. Okay, so maybe we can use the same a here. The greatest common divisor of a of 41 and 25,855 is indeed 1.
Yeah.
So that's good. Let's see if we can find the period. The period of 41 mod 25,877 is 3,192.
That's good. We wouldn't have been able to find that at all.
Right. It takes 3,192 times through
For it to repeat itself.
for it to repeat. And a to the r over 2. Oh, sorry. I scrolled down way too far. Am I on camera here?
Yeah.
We just need this not to be 0. So we're good. And so now we should find the 2 primes. 113 and what was the other one? 229.
Cool.
There we go. All right. So with 3-digit primes, we've been able to do it. So let's do on the next video. Let's go up to some much larger primes and see if Mathematica can still break the code.
Okay.